Hello friends, we are starting a new video. The topic of today's discussion is about number representation and arithmetic operations. Now trust me, this is one of the most easiest topic in your COA subject where you can score almost 100% of the marks. And again, trust me, this is the topic where 90% of the students fails, 90%. Just because they think or they feel this is the easiest topic and we shall practice less on this topic. But you should not. You have to practice more and more, then only you can understand the topic very well. So in today's lecture, we'll try to give some shortcut tricks also. How can you solve some arithmetic operations? Specifically whenever we talk about 2's complement operation, we'll give some tricks also. So topic of today's discussion. Today we'll discuss about number representation and arithmetic operations. Now, if I talk about number representations, then I believe you have already gone through different types of number representations in your previous semesters or maybe in class 10 or 12 also. What are the different types of number representations you have gone through? Maybe you have gone through binary number representation, decimal number representation, octal, hexadecimal, and so on, right? Different types of number representations you have gone through in your previous semesters or in your previous years. Now, in today's lecture, we will mostly focus on binary representations only. Why binary representation? Binary is the only number representation which we will use repeatedly in this course, COA, Computer Organization and Architecture. And you know computer understands only 0 and 1. So our main focus will be only on binary number representations mostly. Fine. So just a quick revision. In number representation, the most famously used representations are number one, decimal number system. What is a decimal number system? A number system which can be represented using some digits. What are the digits? 0 to 9. So we can use any digit to represent the number. And how to represent a decimal number? Each digit has a position value in terms of power of 10, right? If I write 123, then 1 into 10 square, 2 into 10 to the power 1, 3 into 10 to the power 0. So finally we'll sum all these things and we'll get 123. We know all these things, right? This is nothing new for you. Next is binary number system, and binary number system is also not new for you. This is also you already have gone through many times, right? In binary number system, how we deal with? The first thing is we have only two digits to represent the number. What are the two digits? Either 0 or 1, right? And just like your decimal number representation, here also each digit has a position value. In decimal, the position value was in terms of power of 10, but here in binary representation, the position value is in terms of 2, right? So if I give you a number, say 101, and if I ask you just convert this number to decimal or represent this number back into decimal, how you will do it? Just same way, whatever you have done with decimal number, almost same thing. The only difference is here we will use 2 to the power, not 10 to the power. So 101 will be represented as 1 into 2 square, 0 into 2 to the power 1, and 1 into 2 to the power 0. Fine. So we'll come from right to left actually. If you see here, this is the 0th position, 1 position, 2 position. So 2 to the power 0, 2 to the power 1, 2 square. Right? Like this we go ahead. So next, if you know about binary numbers, we have two types of representations we can have in binary numbers also. What are those? One is the number may be an integer number, or second one is the number may be in a floating representation or floating number, right? In today's lecture, we'll focus on integer number only, not floating numbers. So we'll discuss about integer number. Again, in integer, we can have two different types of representation. What are those? First one is unsigned integer, where there is no sign bit or there is no sign, whether it's positive, negative, we don't know. We have the number and we know how to convert it back to binary. That's it. Just like our previous example, right? This one is unsigned. We don't know whether this is positive or negative. We got a number and we just converted back to decimal. We don't know what it is, whether it's positive or negative, right? Unsigned means there is no sign, right? And whatever we have gone through till date, most of the time we have gone through unsigned number only. We know mostly about unsigned numbers only. Suppose if I ask you to convert 0000 to decimal or 0 to binary, then we know in 4 bits how to represent it. This is unsigned. If I ask you convert 15 to binary, we know how to convert it, right? Using 4 bits, I can represent 0 to 15, and this is how we already know. So I don't want to waste your time on discussing all these basic things. So we know about unsigned numbers very well. Fine, that is not an issue. Now the actual point of discussion, or the point where you have to focus on today's lecture, is about signed integer. So for some of you, this can be a new topic where we'll deal with signed numbers, now not unsigned numbers. Means if I convert something to binary number, before converting we'll see whether the number is positive or negative. Fine. For signed number representation, we have three different techniques. First one is sign and magnitude, second one is ones complement, and third one is twos complement. So we may have some other techniques also, but these are the three major commonly used signed integer techniques. Fine. So we'll see all these techniques one by one. Now before we move on with all the topics or each topic, there are a few points you should note it down. Number one, in signed integer, one thing you have to notice is that the positive numbers, all the positive numbers have the same bit representation. Whether you are representing in sign and magnitude, ones complement or twos complement, positive numbers representations are always same. Means the difference or the problem is with negative numbers, not with the positive numbers. Positive numbers are very easy to represent. Whatever you have done till date, all are by default positive numbers only. Fine. And two more points you should remember. In all the representations, whether it's sign and magnitude, ones or twos, the negative numbers have different bit representation. Positive numbers, the leftmost bit is 0, the MSB. If the MSB is 0, then you have to understand that the number is a positive number. Fine. If the MSB is 1, means your number is starting with a 1, that means the number is a negative number. So you have to remember these 2 points. It can be in any representation, sign and magnitude, ones complement, twos complement, but these things are common. If it's starting with 0, it's a positive number, so sure shot it's a positive number. If it's starting with 1, then sure shot it's a negative number. We have to note this point. Fine. Next we'll see one by one about all these techniques. First is sign and magnitude. So how to represent anything in sign and magnitude? So as I told you, most significant bit of the corresponding number will be representing your sign. Means suppose you have something to represent in 3 bits. Say you want to represent 3. I asked you to convert a decimal number 3 to binary number. How you will convert? Forget about signed or unsigned. I asked you to convert 3 to binary number. What you will do? You will take 3 bits. Fine. 3 bits or 2 bits you will take. And what you will do? 3 is nothing but 0, 1, 1. Right? 0, 1, 1 is your 3. Fine. If I ask you to represent 4, then what you will do? 1, 0, 0. Right? 1, 0, 0 is nothing but 4 in binary number. Now, in sign and magnitude, what we will do? We have a reserved bit. A reserved bit which will be used in MSB, most significant bit, which will be reserved for sign only. Fine. 1, 0, 0 is your 4. Now I want to make it plus 4. Then you have to put 1, 0 before your number. Means it will be 0, 1, 0, 0. This 0 is reserved for your sign bit. You understood that? If I ask you to represent this number in negative, means I want minus 4. How you will write? 1, 0, 0 is 4, we know. Minus 4 will be 1, 1, 0, 0. Why 1, 1, 0, 0? This 1 represents negative. You understood that? We have some example also, you will understand it better. See the table, what we have. See here. So we know 1, 1, 1 is what? 7, right? 1, 1, 1 is 7. If I ask you to write plus 7, then you have to put 1 additional 0 here. In sign and magnitude, this is how sign and magnitude works. So you have to take 1 additional bit. Plus 6, how we write? How we write 6? 1, 1, 0, right? So if I ask you to write plus 6, then write 1, 0 before 1, 1, 0. If I ask you to write say minus 3, how we write 3? 0, 1, 1, right? This is 3. Now I want minus 3. So what we'll do, we'll put 1 before 0, 1, 1. 1 means negative. You understood that? This is how it works. So I hope it's clear for you how sign and magnitude works, or how we can convert any number to sign and magnitude. Fine, right? So one thing we have to understand, that in sign and magnitude, the MSB represents the sign, right? And all other bits represent the magnitude. Fine. And as I told you, 0 represent positive and 1 represent negative. I hope that's clear. Now we'll discuss about ones complement. The second technique of, or second approach to convert any decimal number, any signed decimal number to binary is ones complement. So in ones complement, what we will do, this is one of the easiest technique. What we used to do is, we used to flip all the bits. Means, see the table. We know 7, right? We know plus 7. We know plus 7. What is plus 7? We already know. 0, 1, 1, 1. 7 or plus 7 is almost same, right? Only this 0 is different here. So 7 or plus 7 in 4 bits are 0, 1, 1, 1. Now if I ask you to make it minus 7, as I told you, positive numbers are fine only. It's same with your unsigned integer. So there is no problem with positive numbers at all. Problem is with negative. Now if I ask you, convert this plus 5 to minus 5 using ones complement. Now we know how to convert using sign and magnitude. Now if I ask you to use ones complement, how to convert that? We know plus 5 in 4 bits, right? 0, 1, 0, 1. Now in ones complement, what we do is, we just flip the bits, all the bits. Means wherever I have 0, I will make it 1. Wherever I have 1, I will make it 0. That's it. See here, the LSB is 1 here. In minus 5, it will be 0. It is 0 here, it is 1. 1, 0, 0, 1. Means everything you just reverse it. All the bits you just reverse. That's the way ones complement works. I think that's fine. That's clear for you. So next, yeah, these are the examples we have. If it is plus 6, 0, 1, 1, 0, then minus 6 in ones complement, what it will be? Can you tell me? Yeah, it will be 1, 0, 0, 1. That is minus 6. Fine. And yeah, so we'll discuss about the next technique or next approach now, which is twos complement. Now this is the most important approach which we will follow throughout the COA course. You have to put more concentration on twos complement. Fine. Why twos complement? We'll see that. I'll tell you in upcoming minutes, upcoming classes. So in sign integer, whenever we convert using twos complement, how to deal with that? There are several techniques for that. We'll see all these techniques one by one. The first technique is, whatever number I have given to you, convert it back to ones complement. Please pay attention. Whatever number I have given you, say plus 7 I have given, first make it minus 7 using ones complement. Fine. After that, you have to add plus 1 with the number. Then the final result will be in twos complement. Let me take one example. Say I asked you to make plus 6 to minus 6 using twos complement. What is the official way to do that? First of all, you convert plus 6 to minus 6. This is plus 6. We know that this is plus 6, right? 0, 1, 1, 0. First of all, you have to convert this plus 6 to minus 6 using ones complement. So if you do that, what we will have? All the reverse bit will have, right? 0 to 1, 1 to 0, 1 to 0, 0 to 1. So this is the number in ones complement. This is minus 6 in ones complement. But in twos complement, that's not the end. What we'll do? We'll add plus 1 with the result, whatever result you got using ones complement. So we'll add plus 1 here. Every time plus 1. This is constant. So don't be confused. Wherever you are converting any number, decimal number to twos complement, every time you have to convert it back to ones complement first and plus 1 every time. So if you add plus 1, then how it will look like? 1, 1 is 0. Then you will have one carryout bit. So 1, 0 is 1, 0, 0 is 0, 1, 0 is 1. So this is your minus 6 in twos complement. I hope that's clear for you. Now we'll see a table. So this is plus 7. Plus 7 is 0, 1, 1, 1. If I ask you to write or represent minus 7 in twos complement, what we will do? As I told you, first of all, I will convert, or I will make minus 7 using 1's complement by flipping all the bits or by changing all the bits. Then I will add plus 0001. Then finally we will get this one 1001 is minus 7. If plus 6 is this, minus 6 is this. So you follow the approach, you will find this, you will understand this table. Fine. So now I will tell you a shortcut trick to convert from any decimal number to 2's complement. Please pay attention and try to remember the shortcut trick. This is the official way to do, I know, but there is a shortcut trick also. If you use that trick, then within few seconds only you can easily convert it. No need to convert it back to 1's complement, then again to add zeros, add 1 and then finally get the result. So I'll tell you the shortcut trick. What is the trick? Get the positive number first. Fine, get the positive number first. And then from LSB, keep all bits same until you encounter the first 1. Once you get the 1, flip all other bits. I think it's confusing for you, right? So let me explain with the same example, this one. So once I have plus 6, this is the plus 6 I have. So what is the traditional way to convert? I have flipped all the bits to get 1's complement, then 1, I have added 1 to get the final result, right? So in the shortcut trick, no need to do these things at all. Fine, we will directly get from this to this. So if you know plus 6, this is plus 6 we know, right? So what this shortcut trick says is, you start from LSB, not from MSB, means from rightmost bit you have to start in the shortcut trick. So what is my rightmost bit? It is 0. Then continue with the left hand side, means you have to move left. So what is the next bit? You have 1. So what is the goal? The goal is to get the first 1, not 0. So where is the first 1 I am getting? Here. So until and unless I am getting 1, I will keep the bits as it is. So 0 and 1 will be as it is. Fine. 0 I am putting as it is, then 1 also I am putting as it is. Until and unless I get first 1, I will put everything as it is. There may be multiple zeros. Maybe there are 3, 4 more zeros. So I will put 0, 0, 0, 0 only. Same thing. Until and unless I get 1, till 1 I will put it as it is. After that, whatever bits I have, I will just flip it. I will just reverse it. I have 1 here, I will make it 0. I have 0 here, I will make it 1. You understood that? So using this technique, in one step only you can convert. See here, for any other number, say I have plus 5 or maybe plus 4, I will say. Plus 4. What is my plus 4? 0, 1, 0, 0. If you use the shortcut trick, how to convert it to minus 4, I will start from the rightmost bit and I will search for the 1. So first one is 0. So I will keep it as it is in minus 4. 0. Next one is also 0. 0. Next one is 1. Yeah, I got a 1. So till 1 I will put as it is, right? Next, all the bits will be flipped. I have only one bit which is 0, so I will make it 1. That is minus 4. You understood that? So this is a shortcut trick to convert any integer to 2's complement representation. Fine. So next we'll discuss about some more things about 2's complement, some more topics. So what is that? We have to remember some point. Using n number of bits, range of the numbers that can be represented in 2's complement are minus 2 to the power n minus 1 to plus 2 to the power n minus 1 minus 1. That means if I give you 4 bits and if I ask you to represent any binary number, now for unsigned, how many numbers you can represent using 4 bits? 15, right? 0 to so 16, right? 0 to 15, 0 0 0 0 to 1 1 1 1 using 4 bits. So total there will be 16 different representations you can have. But fine, but you have to remember, in 2's complement I cannot represent 16 different numbers using 4 bits. How many numbers I can represent? There is a range. What is the range? Minus 2 to the power n minus 1. This is the lowest number I can represent. 2 plus 2 to the power n minus 1 minus 1. This is the highest number I can represent. This formula is common or applicable for any number of bits. That means if I give you say 4 bits, I am giving you 4 bits and I am asking you how many different numbers you can represent using 4 bits. It will be minus 2 to the power n minus 1, means minus 2 to the power 4 minus 1. So what is minus 2 to the power 4 minus 1? Minus 2 to the power 3, which is minus 8. 2 plus 2 to the power n minus 1 plus 2 to the power n minus 1 is 2 cube minus 1, means 8 minus 1 is 7. Means using 4 bits you can represent minus 8 to plus 7, any numbers which are in between minus 8 to plus 7. You understood that? That means to represent plus 8 in 2's complement, we need 5 bits. You have to remember this. We know plus 8 or 8 we can easily represent using 4 bits for unsigned, right? If I ask you to represent 8, you will take 4 bits only, not 5 bits. But in 2's complement, plus 8 cannot be represented in 4 bits. You understood that? You need 5 bits only. So similarly, all these things, if you have 6 bits, it will be minus 2 to the power 6 minus 1 to plus 2 to the power 6 minus 1 and so on. Fine. Now we'll have a final comparison table. So we have gone through sign and magnitude, 1's complement and 2's complement. So if you see here, for positive number representations up to plus 0, everything is same in all the representations. Fine. These are the numbers. In sign and magnitude, this is plus 7. In 1's complement also plus 7. In 2's complement also it's plus 7. Up to plus 0, this is same. There is no difference only. The differences are in negative numbers. Fine. But one thing you can see, the common thing we have this MSB. For all the positive numbers, the MSBs are always 0, and for all the negative numbers, the MSBs are always 1 for all the representations. This is the only common thing we have for negative number representations. Otherwise, if you see, 1,000 is minus 0 in sign and magnitude. Why it's minus 0? We know. In sign and magnitude, the last or MSB will be for sign, right? 0, 0, 0 is 0. This 1 I am putting here means minus 0. This is minus, right? Again, same number, if you see, in 1's complement, it's minus 7. Why it's minus 7? What is plus 7? 0, 1, 1, 1. So, minus 7 in 1's complement will be what? 0, 0, 0, 1. So, 0, 0, 0, 1 is minus, yeah, it is, sorry, 1, 0, 0, 0. 1, 0, 0, 0 is minus 7 in 1's complement. Fine. But this is in 2's complement. If you convert this is minus 8, not minus 7 at all. You understood that? So there are the comparison of all the different techniques, how it looks like. I have explained all the techniques separately, so I believe you can easily convert it. Now if you see from this table, one thing can you notice here? In sign and magnitude, we have plus 0, minus 0. In 1's complement, we have plus 0 representation also, minus 0 representation also. But in 2's complement, we never have minus 0 concept. We have only plus 0. You understood that? So it's almost meaningless, or it's baseless to use plus 0 and minus 0. 0 is 0, right? Why will use plus 0 and minus 0? For other numbers, it's fine. We have to use either plus or minus. But for 0, if you use plus 0 and minus 0, it's meaningless or it's baseless. That's why we prefer to use 2's complement every time, where I don't have any minus 0 representation. I will never get minus 0. That's why we mostly use this technique, not this or not this. Fine. Now I will tell you one more trick. Please pay attention. Using the trick, you can easily convert any decimal number to 2's complement within few seconds. And again, if I ask you to convert any decimal number to 2's complement, it's fine, it's easy, you can do it. The problem is, if I tell you the number is already in 2's complement, I given you a binary number which is in 2's complement, and if I ask you to convert it back to decimal representation, it's very difficult in 2's complement. You don't know how to convert it back to decimal. So using the trick, you can do both the things. So you can convert any decimal number to 2's complement or vice versa. For that, what you have to do? Please pay attention, and you can take a note also. This is very helpful for your future course also. Say you have 4 bits to represent any number. So what we will do is, in 2's complement arrangement, we will write like this: 2 to the power 0, 2 to the power 1, 2 square and minus 2 cube. Just notice one thing here. If I ask you to represent any number in 4 bits, forget about sign. Then what we do? This is how we arrange, right? 2 to the power 0, 2 to the power 1, 2 square, 2 cube, 2 to the power 4, 2 to the power 5. Like that we continue, right? So same thing we are doing here. The only difference is the MSB will be always negative. Other numbers representations are same with your unsigned number only. Understood that? You can have n number of bits. So it will be 2 to the power 0, 2 to the power 1, 2 square, 2 cube, 2 to the power 4, 2 to the power 5. All these represents, all these positions will be positive only. Only the MSB or the last or the final value will be negative, minus 2 to the power m. Rest all will be positive only. Here if you have say 5 bits, then what you will have? 2 to the power 0, 1, 2, 3 and minus 2 to the power. The last one is only negative, rest all are same. So I hope you can easily arrange this bits, right? You can easily arrange this number. This is nothing very difficult. So next what? Once you can arrange it like this, then you know how to convert any decimal number to 2's complement or from 2's complement to decimal. Now it's very easy for you. Let me tell you how. Say I have given you one number 110100. This is the number I have given to you. Check it very carefully. 110100. This number I have given to you. And I told you this number is in 2's complement. This is not a normal binary number. This number, whatever I have given to you, is already in 2's complement. Now tell me the corresponding decimal value for this 110100. So how to do that? How many bits are there? Check it. 1, 2, 3, 4, 5, 6. That means I can arrange the numbers like this: 2 to the power 0, 1, 2, 3, 4, 5. So 0 to 5. 0, 1, 2, 3, 4, 5. So last one will be negative, rest all are positive. 2 to the power 0, 1, 2, 3, 4, 5. Fine. So minus 2 to the power 5 means what? Minus 32, right? Rest 16, 8, 4, 2, 1. Now put all these bits in the position, you will get the result. So what do we have? 110, 100, 110, 100. Now check the positions. What you have here? Minus 32 into 1. So minus 32, 16 into 1, 16, 8 into 0 is 0, 4 into 1 is 4, 2 into 0 is 0, 1 into 0 is 0. So finally you add all these numbers, you will get minus 12. So this is nothing but minus 12. You understood? So although this topic is very simple, but most of the students, 90% students fails here. If anyone asks that convert this number back to decimal when this is in 2's complement, they don't know how to do. And end of the day, what they do, they just simply convert it back to a normal unsigned binary number. From unsigned to, sorry, they think this is unsigned and they just simply convert like unsigned. You understood that? Now we have one more number, 01101. So here how many bits are there? Same, 0, 1, 2, 3, 4, 5. So same representation I can have. Put the bits 0, 1, 1, 1, 0, 1. Now minus 32 into 0 is 0, 16 plus 8 plus 4 plus 1. So this is 29. This is plus 29. If you see, we have 0 here, so obviously this will be positive. We have 1 here, obviously this will be negative. We have already gone through. So I think this is very clear or very easy for you to convert any binary number which is already in 2's complement to decimal representation like this, right? Now the reverse way, if I give you some decimal number, say I have given you minus 34 and I asked you to convert it back to 2's complement. Now you already know two different methods, right? One method, just get plus 34 first, then make it in 1's complement and then add plus 1 with this. Whatever result you will get, that is minus 34. That was one way. And second trick, whatever I said was make it to plus 34 and then from right hand side you search for the first 1 until and unless you get 1, keep all the bits same, rest all the bits, you just reverse it. Those are the two techniques I have already discussed with you. So this is the third technique or the third shortcut way you can use. What you can do? What I need? Minus 34, right? So you have to know here, you have to be a little bit careful. So to get minus 34, how many bits I need? One way is to get the formula. We have the formula, right? So in the formula we have the range. So from there also you can easily find out how many bits we need. But if you don't want to remember the formula, just you want to convert it, then how you will do? I need minus 34. That means if I use 0, 1, 2, 3, 4, 5, so if I take only 6 bits, then what you will have? Here I will have minus, this one will be minus then, right? So minus 32. So the maximum representation I can have minus 32, but I need minus 34, right? That means I need one more bit. So here I will put one more bit for 2 to the power 6. Minus 2 to the power 6 is minus 64. So now arrange all these things, minus 64, 32, 16, 8, 4, 2, 1. Now you make minus 34 out of this arrangement. So how to make minus 34? So it will be minus 64 plus 16 plus 8 plus 4 plus 2 is nothing but minus 34. So just put 1 on this. we know minus 64 plus 16 plus 8 plus 4 plus 2 is minus 64. So put 1 only on those places and rest all the places will be 0. So the final result is 1 0 1 1 1 1 0. I hope that's clear for you. Fine. So next we'll see some arithmetic operation, addition of any two binary numbers. So this is very known to you. If I give you any two bits to add, 0 0 is always 0, 1 0 is 1, 0 1 is also 1, 1 1 is actually 1 0, right? We know that 1 1 is 0 and carry out bit is 1. We already know. So this is, I don't want to waste time on this. So I don't want to discuss all these things also. Now in 2's complement, this is the important thing. Normal unsigned addition we already know. We have gone through many times from class 10 12 only we are doing unsigned addition. But how to add two numbers when we talk about 2's complement? Fine, we'll see how to do that. Say I asked you to add plus 2 and plus 3. So how to do it? First you make plus 2 in 2's complement. This is plus 2, plus 3 in 2's complement. This is plus 3. We already have the representation in right hand side for your simplicity. And then you just add all the bits just like unsigned numbers only. This is not a difficult thing. 0 1 is 1, 1 1 is 0, you have a carry out bit, so 1 0 plus 5. Fine. Next I asked you to add plus 4 with minus 6. How to do that? Same thing. Plus 4 we know how to represent plus 4 in 2's complement. We know how to represent minus 6 in 2's complement. Then add bit wise like this. Fine. Next minus 5 plus minus 2. So I know how to represent minus 5 here. And I know how to represent minus 2 here. Just add it. 1 0 is 1, 1 1 is 0, and then carry out bit is 1. So 1 1 is 0, carry out bit is 1. So 1 1 is 0, 1 is 1, but you have a carry out bit 1 here, which is ignored. Just stop here and think it. We are ignoring the carry out bit. Now my question is, can I ignore this carry out bit every time? No. We cannot ignore this one every time. Here I am ignoring my 1, but still I am getting the result. It's fine. But remember, we cannot always ignore the carry out bit. I will come to that in the next slide. So before that, one more example I will see. Plus 7 and minus 3 I am adding. So plus 7 I know, minus 3 also I know how to represent. And then I am just adding bit wise. So here also I am ignoring the carry out bit or the final. So here also I can ignore the bit. Still I will get the correct result. So I am ignoring the carry out bit. Now when to ignore the carry out bit and when not, we'll discuss in the upcoming slides. So before that, let's see how to subtract two numbers in 2's complement. Addition is fine. Subtraction, how to do the subtraction. Subtraction is also as like your addition only. You can say this is addition only, nothing else. So what we have to do is, suppose I asked you to subtract minus 5 from minus 7. What I said? Minus 7 minus minus 5. Then this minus 5 will become plus 5, right? Minus 7 minus minus 5 means it will be ultimately what? Minus 7 plus 5 only. So once you get minus 7 and plus 5, just add all the bits and you will get the result. Fine. Similarly, if I ask you to minus 1 from minus 7, means minus 7 minus 1. So what you have to do is, you have to add minus 7 and 1. So this minus and plus will become minus. So this is nothing but minus 7 plus minus 1. So minus 7 minus 1 if you have, just add these two numbers. So as addition only, this is nothing new. Similarly, if I ask you to subtract minus 3 from plus 2, what I will do? It will become what? Plus 2 minus minus plus. So plus 2 plus 3 only. So plus 2 plus 3. You just add all the bits, you will get the number. Fine. Now we will discuss about the carry out bit, the final carry out bit, whether we shall ignore it or not. So before going for the conclusion, we should know one concept called overflow. Please pay very attention on this topic, because this is one of the simplest topic, but most of the students fails here. They don't know what is overflow. They don't know how to, when to consider the carry out bit and when to not. So what is overflow? So arithmetic overflow is a condition where, suppose you are adding two numbers. Number one, first both the numbers are in 4 bits. Please pay attention. You are adding two numbers having 4 bits representations. But when you add these two numbers, the final result, in the final result, you cannot store the final result in 4 bits. You need one more bit. Understood? You need one additional bit to store the final result. That time you need one more bit. So that carry out bit you cannot ignore, and this situation is overflow when the final result is out of the range. Did you understand that? Suppose I asked you to add, say, forget about sign number. I asked you to add plus 8, 8 plus 9. I asked you to do 8 plus 9. Now to represent 8, how many bits you will take? Obviously 4 bits. To represent 9, how many bits you will take? 4 bits. Now if you add these two numbers, 8 plus 9, what is the final result? 8 plus 9 is 17. Now the question is, can you represent 17 in 4 bits? No, because we know the range. What is the range for unsigned number? 0 to 15 only I can store, or I can represent using 4 bits. So we need one more bit to store this value 17. So that time, that carry out bit, whatever we are getting, we cannot ignore. We have to consider that because we need one additional bit. And this situation is nothing but overflow. When the final result is out of the range is known as overflow. Fine. So I hope you understood what is overflow. So mostly in 2's complement, overflow occurs when two positive numbers are added. You are adding two positive numbers, but the final result you are getting as a negative number. That means you should know that if you add two positive numbers, obviously the final result should be positive, right? It cannot be negative, but it's appearing as negative. How you will know it's a negative or positive? By seeing the MSB. If it is 1, we know it's a negative number. So if this is the case, then we have to consider the carry out bit. Fine. And also, if two negative numbers are added which result in a positive number, if you are adding two negative numbers but in the final result you are getting a positive number, means there is an overflow in 2's complement. These are the two situations. Fine. And one more thing you have to note it, so make it very clear. Maybe for the first time you will know this thing, that the carry out bit is not always only 1. Don't think that the final carry out bit is always 1 and we have to decide whether we shall take it or not. No, sometimes this carry out bit is 0 also. Even in some situations you have to consider this 0 also. We'll see all these things in upcoming slides with some examples. It will be more clear to you. So now we'll see some arithmetic operation. We'll try to understand how overflow occurs. What I want to add? Plus 7 and plus 4. Just add it. This is my plus 4 and plus 7. This is my plus 4. If you add this, what you are getting? 1 0 is 1, 1 0 is 1, 1 1 is 0, then here I have 1. So if you see, if you convert this number to decimal number, what you are getting? First of all, this is a negative number. We have 1 here in MSB. And if you convert it back to 2's complement, you will get minus 5, which is incorrect. Fine, this is incorrect. This is not correct. Means overflow. Second example, minus 4 plus minus 6. Just do it. Minus 4 and plus 6 if you add, this is minus 4, this is minus 6. If you add, what you are getting? 0 0 is 0, 0 1 is 1, 1 0 is 1, 1 1 is 0, and carry out bit is 1, which we ignore most of the time. If we are ignoring that, then what we are getting? Plus 6. But what shall we get? Minus 10. This is incorrect, right? So we have to know that there are some overflows. That's why we are getting incorrect results in these situations. Now, as I told you, the first or official way to determine overflow is to see the range. What is the range? I have plus 4 and plus 7 and plus 4. The final result is 11, plus 11, and I cannot represent plus 11 using 4 bits because we have the range, right? Using 4 bits, what is the maximum positive number I can represent? It's plus 7, not plus 12. So we shall know that I need one more bit. Which bit I will consider? The final carry out bit. Similarly here also. This is the official way to determine. Next, one shortcut trick is there to determine. I will not say it's a shortcut. This is another official way to determine whether there is an overflow or not. If there is an overflow, you have to consider the carry out bit. If no overflow, ignore the carry out. Understood? Now, how to determine if there is an overflow or not? Please pay attention. What I will do is 1 0 is 1. Will go bitwise. 1 0 is 1. So here, what is the carry out bit for first two addition? The carry out bit is 0. So I will note it somewhere 0. This is the first carry out bit. Fine. Next is 1 0 is 1. What is the carry out bit I am getting from here? Here also no carry out bit, so 0. Now 1 1 is 0. So there is a carry out bit. I am writing 1. So 1 0 is 1. There is no carry out bit. Here it's 0. Fine. Similarly, here you see 0, 0 is 0, so next carryout bit is 0. 0, 1 is 1, no carryout bit, so 0. 1, 0 is 1, no carryout bit. 1, 1 is 0, we have a carryout bit 1. Now, see these two things. So here, once you note down all the carryout bits like this for all the bit additions, then you have to notice one thing. The first two carryout bits from MSB you have to check. What are the first two carryout bits? Here I have 0, 1 and here I have 1, 0. Remember, once you note it down like this and the first two carryout bits are either 0, 1 or 1, 0, then we will say that there is an overflow. You understood that? If these two bits are either 0, 0 or 1, 1, means if both are same, either 0, 0 or 1, 1, then we will say there is no overflow. If you are getting any carryout bit, just ignore it. You cannot consider that. But if it is 0, 1 or 1, 0, means there is an overflow. No matter which carryout bit you are getting, it may be 1 or 0 also, you have to consider that. I hope that's clear for you. Now we'll see some more example. Yeah, this is the trick whatever I said. So what I will do, all the carryout bits I will note. Then if the first two carryout bits are 0, 0 or 0, 1, then there is no overflow. Ignore the final carryout bit. If the first two bits are 0, 1 or 1, 0, then there is an overflow. So you have to consider the final bit. Fine. In 2's complement addition, sometimes because of overflow, we need to consider the final carryout bit, which can be even a 0 also. I told you, right? So we'll see all these things in the next few examples. It will be more clear to you. See here, what I am adding? -7 and -2. Okay, I will add it. So -7 I am representing here, -2 I am representing here, and just add it. 1, 0 is 1, 0, 1 is 1, 0, 1 is 1, 1, 1 is 0, and carryout bit is 1. Fine. And I have noted down all the carryout bits like this. 1, 0 is 1, so 0, 0, 1 is 1, 0, 0, 1 is 1, 0, 1, 1 is 0, 1. So what you can notice here, the first two bits are 1, 0. Means we have to know that there is an overflow. Means this carryout bit I have to consider. The final answer will be 1, 0, 1, 1, 1, not 0, 1, 1, 1, because there is an overflow. You understood that? Next example is see +5 and +2. This is +5, this is +2. So I am adding, so there is a carryout bit as 0. I told you in 2's complement this 0 also sometimes very important. So you cannot ignore just because this is 0 in the final carryout bit. I will tell you why. So if you add this, if you see the first two bits, these are 0, so we know there is no overflow. You can simply ignore this 0. So final result will be 0, 1, 1, 1. Next one. See here what I have, -3 plus -5. This is -3, this is -5. Now you add it, 1, 1 is 0, and then 0, 1 is 1. So everything I have added, and I have noted down the final carryout bits, all the carryout bits. What are the first two carryout bits? 1, 1. 1, 1 means there is no overflow. So you have to ignore this one. So final result will be 1, 0, 0, not 1, 1, 0, 0. Understood that? Now we have one more example, -1 plus -6. So this is -1, this is -6. Similarly, I have added all the bits and I have noted down the carryout bits. So first two carryout bits are 1, 1. So there is no overflow. Even if we are getting a 1 here, we will ignore it. So the final result will be 1, 0, 0, 1. See here, I am adding -8 plus -7. So -8 plus -7 I am adding, and finally we are getting finally we are getting 1, 0 as the first two carryout bits. So if it is 1, 0 means we have to know that there is an overflow. We cannot ignore the carryout bit. So final result will be 1, 0, 0, 1. Fine. Next you see here. So here we are adding -8 and +7. There is 0, 0 as the first two carryout bits. So there is no overflow. We are simply ignoring it. Next, please check it very carefully. This one is one of the most important examples. So here what we are adding is +7 and +6. This is +7, +6. We are adding 1, 0 is 1, 1, 1 is 0, carryout bit is 1. So 1, 1 is 0, 1 is 1, carryout bit is 1. So 1, 0 is 1. So what is my final carryout bit? 0. There is no carryout bit, or 0 is the carryout bit. If you note all the carryout bits, what I am getting here? 0, 1, 1, 0. So first two bits are 0, 1. If 0, 1, we know there is an overflow. Right? We know there is an overflow. Now the question is, what is my carryout bit? Final carryout bit? 0. Then what to do? Shall we consider or not? I told you in 2's complement this 0 also is very important like 1, so you cannot ignore this 0. Final result will be 0 1 1 0 1, not 1 1 0 1. We have to consider this carry out bit. If you ignore this 0, then what you will get? 1 1 0 1, which is a negative number, right? But plus 7 plus 6 cannot be negative. So the final result is 0 1 1 0 1. That's why you have to note this 0 also in 2's complement. In unsigned, it does not matter for 0, but for signed, 0 also matters. So you have to consider that. Fine. So I hope it's clear for you how to add two numbers in 2's complement and how to subtract two numbers in 2's complement, what is overflow, when to consider carryout bit or not. Fine. So the last topic of today's discussion is about sign extension. Means how to extend the sign. If I ask you to extend the bits for any unsigned number, it's very easy, right? If I ask you to represent 3, then how you will represent? Maybe 1 1, right? 1 1 is 3. Yes. Now if I ask you to represent this number using 5 bits, then what you will do? You will add all the zeros left hand side, right? This is how it represents. Say 1 1 is 3 using 2 bits. If I ask you to make it into 5 bits, then what you will do? 0 0 0 1 1. This is 3. If I ask you to add more bits, so you will add all zeros, right? For unsigned. But for signed, you cannot simply add zeros. So what you have to do is, you have to check the MSB or the sign bit. If your MSB is 0, say this is the number 15213. So this is the number 15213 we have using some number of bits. Now I asked you to extend the bits to some other, maybe few more bits you have to add. Now for unsigned, every time we'll add zeros, no matter what the number you have, right? Every time we'll add zeros and the bit will be extended. But for signed numbers, you have to check the sign bit. What is my sign bit or the first bit? MSB is 0. If it is 0, then we have to add all zeros. If it is 1, then we have to add all ones. Understood that? Then only it will be same value. Otherwise, it will be a wrong value. So this is how we can extend the bits. So that's all about today's class. I hope you liked the video. If so, then please subscribe to my channel, share the video, and also if you have any suggestion, please put in the comment section. Thank you everyone.